Hello everyone, my name is Proctor, and today we're going to be talking about advanced hypothesis testing and performing a paired data analysis. We're going to be using this iris flower dataset, and so this is a very interesting dataset that comes from a British statistician and biologist, Ronald Fisher, in his 1936 paper. And so we have our sepal length, our sepal width, our petal length, and our petal width for three different species of iris. And so we're going to be using this to perform our paired data analysis. So in this analysis, we examine the sepal length and the sepal width of iris setosa flowers, and we're determining if there is a significant difference between these two related measurements on the same flowers. The paired t-test was chosen for this comparison because it's suitable for analyzing two measurements from the same subjects. And our test helps determine whether the average difference between sepal length and sepal width is significantly different from 0. So let's quickly go over this code here. So first we load our CSV, our iris dataset, then we get the width and the length of the sepal using from our data frame. And then we're going to perform a t-test and get the t-statistic and p-values using our t-test rel function. And then we're going to compute the differences from the lengths and the widths by performing this simple calculation. And then we're going to use this difference to compute the Shapiro-Wilk test for normality on our differences. So we basically pass in the difference as an argument into our Shapiro function. This returns our p-value for normality, and then we print out that result. We have our histogram of differences for the sepal length versus the sepal width, and then we also have our quartile plot for the differences as well. And so let's take a look at our results that we have printed out from our Python code. And so we have our paired t-test along with the histogram QQ plot for the differences between sepal length and sepal width. The paired t-test results show a t-statistic of 35.008 and a very small p-value, which indicates a highly significant difference between sepal length and sepal width. Our Shapiro-Wilk test for normality has a p-value that's really small, and this suggests that the differences does not follow a normal distribution. Our histogram shows the distribution of the differences between sepal length and sepal width with the shape that appears somewhat bimodal, and this indicates the presence of two peaks in the dataset. The QQ plot compares the quartiles the quantiles of differences to a theoretical normal distribution. The points deviate from the red line, especially on the tails, and this supports that the data does not follow a normal distribution. Overall, our paired t-test indicates a significant difference, but the non-normality of the data as shown by the Shapiro-Wilk test and QQ plot suggests that the assumptions underlying the t-test are probably not fully met. So let's quickly go over our results here. So in our study, the Shapiro-Wilk test was used to check for normality, and this revealed a p-value that was small, and this indicates that the differences between sepal length and sepal width do not follow a normal distribution, and this suggests that the paired t-test may not be the best test, and a non-parametric alternative might be better suited. And so the t-test results showed a significant difference between sepal length and sepal width, but the deviation from normality, as shown in our visualizations, challenges the validity of these results. And so our analysis highlights the importance of carefully evaluating assumptions to ensure accurate conclusions. And so we use Python's capabilities for hypothesis testing and performing data visualizations. Thank you for listening. That is all.